The given data of this question is, as in this question, there is a saturated refrigerator R134A vapor at 160 kilopascal. That means pressure P1 is given, that is 160 kilopascal, at the rate of 2 cubic meter per minute, so that the V1 dot is given, that 2 cubic meter per kg per minute. And this refrigerator R134A vapor is compressed steadily by an adiabatic compressor to the pressure P2, that is 900 kilopascal. So this is all our given data. So what we have to find out, we have to find out the minimum power input to the compressor. Minimum power input we have to find out. So here's our solution start. As first of all, that the power input to an adiabatic compressor will be minimum when the compression process is reversible. So the power input is minimum to an adiabatic compressor when the compressor process is reversible. So for the reversible adiabatic process, we have S2 equals to S1. So other values we get from the refrigerant tables, that are table A11 through A13. So for as the, at initial state our pressure P1 is 160 kilopascal and saturated vapor. So at the value of V1 equals to Vg at 160 kilopascal is equals to 0.12355 cubic meter per kg. This value we get from the table, and the H1 that equals to Hg at 160 kilopascal, which is equal to 241.14 kilojoule per kg, while S1 equals to Sg at 160 kilopascal, so this equals to 0.94202 kilojoule per kg into Kelvin. So now from the pressure P2, which is 900 kilopascal, as our S2 is equals to S1 because of reversible process. So from this we get the value of H2. So this equal to 277.12 kilojoule per kg. So also we can find the rate of a mass by using this formula. Now putting their values, that value is given, which is 2 cubic meter per minute divided by U1, that is 0.12355 cubic meter per kg. So by solving this it equals to 16.19 kg per minute, as we want in kilojoule per second, so it equals to 0.2698 kg per second, in we want in kg per second. As there is only one inlet and one exit, so our rate of a mass of m1, which is equals to rate of mass of m2, so that equals to rate of a mass. So we take the compressor as the system, which is a control volume size, since no masses since mass crosses the boundary. So we use the energy balance for this steady flow system in the rate form. So here we use the energy balance relation for steady flow system, and it expressed in rate form. So the rate of net energy transfer by heat and work and mass, that equals to the rate of change in internal kinetic energy, potential energies, etc. As this is a steady flow, so this equals to 0. So this becomes the rate of net energy in equals to rate of net energy out. So this becomes the input power plus the rate of a mass into H1 rate of a mass into H2. Since our Q dot is approximately equals to our change of kinetic energy, that approximately equals to change in potential energy, and that approximately equals to 0. So our work, the power input is m dot H2 minus H1. So substituting the minimum power, now we substituting the values. So the minimum power supplied to the compressor is, this is the minimum power input. Now putting the values, 0.2698 kg per second into 277.12 minus 241.14, and the unit is kilojoule per kg. So by solving this, it equals to 9.71 kilowatt. So this is the minimum power input to the compressor, which is our required answer. So thank you so